Okay, let's do lab 20, part 6.4, which is the very last part of lab 20. So we're using half of our DG403 for this. So this is a switched capacitor filter. This is kind of neat. It's a low-pass filter whose implementation is kind of digital. So let me see if I can explain kind of hand-waving first how it works. First, let's just point. So we have a ticking clock, which is basically setting the time scale for this operation. Okay, so something happens. There's like a shuffling back and forth of charge between two capacitors every tick of the clock. And it turns out our clock in this case will be about 30 kilohertz. And then we have an input signal. And so you know that we're kind of accustomed to frequency-dependent filters taking an input signal and having an output signal which is proportional to the input signal, but its amplitude may be changed and its phase may be changed in a frequency-dependent way. So this circuit will behave just like a low-pass filter, we will see. And it will behave like a low-pass filter whose F3 dB is given by this expression, which is the ratio of two capacitors times this clock frequency, and then with this mysterious factor of 2 pi downstairs. So first, let's just look at what we have set up here. So this is the analog switch, the DG403. So we're using switch 1 and switch 3, which you know are always in opposite states. So if 1 is closed, then 3 is open, and if 1 is open, then 3 is closed. So here's what happens. Suppose initially that 1 is closed and 3 is open. Now the whatever the input voltage is equalizes with this capacitor voltage. So charge is moved on or off this first capacitor, C1, until this voltage equals the input voltage. Then this switch opens, this switch closes. So now charge moves between C1 and C2, but now C2 is much bigger than C1. So charge will shuffle back and forth between C1 and C2 until they have the same voltage. But C2 is much bigger. So C1 can only make a small change in C2 any given time step. This is kind of like, you can imagine that this is like, it's kind of like a bucket, and this is like a bathtub. And you're using a bucket, kind of to try to fill or drain a bathtub. It's not quite a perfect analogy because basically the long-term height of this bathtub is going to equal the long-term height of this bucket. So I'm not sure exactly how to make that analogy work. Okay, so we have some charge stored on this small capacitor, and we have some charge stored on this big capacitor. And we want to be able to observe the voltage on this big capacitor. We want to observe it without perturbing it. So we make use of our friend, the LF411. This is a FET input op amp. And it has an absolutely tiny I bias, right? So we have like I bias was on the order, I think it was like 50 picoamps is the spec, something like that. So it has an absolutely tiny bias current, and that's due to its field effect transistor input. So that means that when we connect this op amp follower, this is just a conventional follower, right? So this 411 is wired up as a follower, and it is following this voltage signal. So the advantage of following it with this FET input op amp is that this input really does draw almost zero current. So like the golden rules say in op amps, inputs draw a negligible current. Well, with a FET input op amp, it really is truly negligible. So then we can observe this with the scope probe. If we plug the scope probe directly over here, then that's 10 mega ohms input resistance, and it would drain the charge off this capacitor relatively quickly. Well, how relatively quickly? I guess we could say the RC time constant would be 10 nanofarads times 10 mega ohms, which I think is 100 milliseconds. I don't know if we want to pause to do that. I think it would be 100 milliseconds. 10 nanofarads times 10 mega ohms. I think that's 100 milliseconds. Okay, so I think it makes sense that the corner frequency, the 3 dB frequency for this, well, first of all, okay, so I think it makes sense that this second capacitor is doing a long-term average of the first capacitor, because you have a big capacitor here, a small capacitor here. This small capacitor, once per clock cycle, is exposed to the input voltage, and then once per clock cycle, this big capacitor is exposed to whatever's on this small capacitor. But again, the small capacitor can only make a small change in the big capacitor per unit time, because right, there's only so much charge that can move back and forth. So I think it makes sense that the output of this circuit will be a long-term average of this input. So that sounds like something a low-pass filter or an RC integrator would do. I think it also makes sense that the corner frequency is going to be proportional to the rate at which we're switching back and forth. And then I think it also kind of makes sense that the ratio of these two capacitances is involved. Okay, so then let's see if we can make more quantitative sense of it. So in pink here, salmon color, I wrote what I think, to my intuition, I actually didn't go through and like carefully go step by step using capacitor math, but you say, what happens to the output? So if you call this is the output, or basically this is a buffered copy of the output. So what happens to the output every time step dt? Well, something can change once per tick of the clock. So here's f clock. And what happens? What happens is that once per tick of the clock, this output voltage, the voltage on C2, changes in proportion to how different is this voltage from this voltage. And this voltage is basically just what this input signal was an instant ago. And how much does this change? It changes by the ratio of these two capacitances, because because a given charge moves back and forth, and the amount of charge needed to put a given voltage on a given capacitor is proportional to that capacitance. So it's the ratio of these two capacitances times this voltage difference is, you say, in a given tick, every time this switches back and forth, this voltage changes in proportion to this voltage difference between here and here times the ratio of these two bucket sizes, right? So there's like the little bucket and the big bucket. And that happens how often? It happens once every tick of the clock. So I think this at least makes intuitive sense, even though I didn't, instead of driving it rigorously, I drove it kind of hand-wavingly. So then you say, okay, now let's write down from memory the differential equation for the RC integrator, right? The RC integrator is the same as the RC low-pass filter. We have our input signal, and then we had a resistor, and then we had a capacitor to ground, and then here's our output. And the differential equation describing the output is the rate of change of the output with respect to time is 1 over RC times the voltage difference between V in and V out. If you remember how we derived that, we were basically just saying You assume that negligible current flows to the output, and then the current flowing into the capacitor is this voltage difference divided by this resistance. That makes sense. So then if you look at this, you want to make these two expressions be the same. You can if you say, what's playing the role of RC? So RC is downstairs here. So instead of RC being downstairs, we have C2 divided by C1 F clock. So C2 divided by C1 F clock plays the role of RC. And then that also makes sense because this has dimensions of time and this has dimensions of time. And then, so you say, okay, if that's true, then 1 over 2 pi RC, you flip this upside down, and you divide by 2 pi, so you have C1 F clock over 2 pi C2. And lo and behold, you have C1 F clock over C2 2 pi. And yeah, I actually got this to work on the first try. I mean, I wrote down Tom's expression, and I said, well, okay, let's kind of reason through what this does every clock tick, and let's write down what the RC integrator does. And I was a little surprised, actually, that it worked on the first try. Anyway. So that's what it's doing, right? So this is actually kind of a neat way of making a low-pass filter. It's the same as the RC integrator, RC low-pass filter. In fact, if you do this with an algorithm on a computer, this is called an IIR filter, which is infinite impulse response filter. This is an infinite impulse response filter. So this actually is. You can actually do this algorithm completely in computer code. You say, every step of the clock, I'm going to say output gets, every tick of the clock, every tick, you say output gets 1 minus epsilon times the current output plus epsilon times the input. So this is a like software low-pass filter that is actually kind of, I've actually used this many times because it's just the code is so simple and it does a pretty good job. So this has the same response as an RC integrator. Every tick of the clock, or every time you go through the loop in your algorithm, you say, okay, the new value of the output is the old value of the output times something like 99%, and then times the input times 1%, or whatever. This is epsilon, this is 1 minus epsilon. So this is a small fraction, this is whatever is left to make 100%. And so it's kind of the same thing. So like C1 over C2 plays the role of epsilon here. Okay. So, and I guess one thing that's neat about this is you can make a low-pass filter that can be precisely adjusted just by changing this clock frequency. That's one thing. And also, you can make a low-pass filter. You have a pretty good flexibility in like how you get your F3dB because you can adjust this ratio of two capacitors, but in software you can adjust this clock frequency. If you're doing this in software, usually you just tune epsilon, and then it's like every tick might mean every sample that you process in kind of a pipeline, and then you can just adjust the value of epsilon to adjust your 3dB frequency. Okay, so I like this algorithm. I've used it many times in code. I haven't really used it as a circuit many times. So anyway, let's take a look. I built it over here. So I guess we can do a brief tour of what it looks like. So what did we plug in? So okay. Waveform generator number 2 is coming into pin 16. So that is this wire right here, top left corner of the chip, the DG403. Then pin 15 is AWG number 1. So that is my clock signal. Well, I'll show you that in a minute. And it goes it goes to pin 15, right? Pin 15 Remember, it opens and closes both of these switches. If this one's closed, this one's open, and vice versa. And then pin 1 is wired to pin 4, and somehow between the two there's a capacitor to ground. So pin 1 over here with this little blue wire is wired to pin 4, and then I have this capacitor to ground, okay, which is a 330 puff capacitor. And then pin 3 goes to pin 3 of the op amp. So here is pin 3 of the DG403, and you'll see it makes its way over there. I'll show you that in just a second. But actually, on its way over there, there's this 10 nanofarad capacitor to ground. So I said the 10 nanofarad capacitor is this kind of inconvenient package. These nylon capacitors are great, but they're not convenient to make connections. So usually you have to put them in their own little columns. So this little wire goes from pin 3 of the DG403 over to the left side of the capacitor. Then that same left side of the capacitor goes over to pin 3 of the op amp, the LF411 op amp. And then the right-hand side of the capacitor has this little black wire going to ground. So this blue row here is ground. And okay, so I think that's everything on, except for power. We have the usual power connections on pins 11, 12, 13, 14 of the DG403. And then this unused pin 10, I connected to ground. You can see where I did that here. So that was pin 3. Pin 2 is the inverting input. It just has feedback from pin 6. So this blue wire goes from pin 6 back to pin 2 of the LF411 op amp. And then that's all except for power. So pin 7 is positive power. So here's pin 7 of the op amp going up to +9. And pin 4 is negative power, so here's pin 4 of the op amp going down to -9. And then pin 6 of the op amp is also our circuit's output, so that is going to scope channel 3. Scope channel 1 is looking at this 30 kilohertz clock, and scope channel 2 is looking at the input signal. Now, let's see what we get. Yeah, let's see what we get. Okay, so what I have here, so the power supplies, I have my usual +5, +9, -9. All three of them are on. Then WaveGen on channel 1, and they're not synchronized. I have two AWG channels not synchronized. So channel 1, I have a 30 kilohertz square wave whose low value is 0 and whose high value is 5 volts. And then on AWG2, I have a 1 hertz sine wave whose amplitude is 5 volts, offset 0. Then let's look at the scope. Okay, so here's channel 1, which is looking at the 30 kilohertz clock. That's kind of hard to focus. We'll look at that later. Okay, so it's there. Channel 2 is the blue or cyan trace. That's what we're sending in. Channel 3 is the magenta or violet trace. That is what we're getting out. And right now they seem to overlap perfectly. This is at 1 hertz. And I predict that F3dB is about 160 hertz. Okay. So let's go up to 10 hertz. Okay, so there's 10 hertz, and we have to zoom in a little bit on the time scale. And you can see a tiny phase shift starting to appear, just ever so tiny. Okay, let's go up to 100 hertz. And we have to zoom in on the time scale. And you can see now a noticeable phase shift appear. In fact, it's beginning to be on the order of 1/8 of a period, 45 degrees. Now, I'm not going to measure it right here. Instead, let's go to our predicted F3dB. Let's go to 160 hertz. 160 hertz. And let's see if this seems like a factor of, okay, this says, okay, this is 5 volts, 4.9. Oh, here, aha. This is 5.0 volts. This amplitude seems to be 3.3 volts. So that's a ratio of 0.66, which is pretty close to the 0.707 we're expecting. That's pretty good. All right. How about the phase shift? It seems like this says, I wonder if I can, oh, look at this. Wait a second. Oh, where's my, I'm having a little trouble measuring this phase difference because it seems like it changes my trigger. Gee. That's kind of annoying. Okay. Oh, okay. I was dragging. So here, if I go from this point to this, oh, that's disappointing. Okay, let's see. Aha! This point to this point. That is a delta x of 863 microseconds. 863 microseconds. And 863 microseconds. And then, meanwhile, the period is 1 over 160 hertz. So I'll say 163 microseconds times 160 hertz. And this is E minus 6. That's 0.138. I guess I was expecting 0.125, so that seems pretty good. So right, that's just a little over an eighth of a period. So it seems like F3dB is a tiny bit smaller than this 160 hertz that I found here. I guess, but yeah. So we're pretty close. All right. I'm going to say that's close enough. We could, like try to measure it precisely. I think it's close. Also, I don't know how close to 330 puff this capacitor is exactly. So I think they're like 10% capacitors. Okay, then let's go up more in frequency because we expect to see this kind of 1 over F behavior. So let's go up to 1.6 kilohertz. 1600 hertz. And then we'll go over to Mr. Scope. We want to zoom in a little. And we should see an amplitude of something like I think it should be 1/10. So this is like 5 volts amplitude. This should be something like 500 millivolts amplitude, I think. Let me blow this up. Hey, that's pretty decent. So I would say, see, I blew this up by a factor of 10. These 2 scales are, oh, you can also see that this is kind of a digitized output. That's also kind of neat because you can see the graininess and the time dimension. So it's because, oh, let me get rid of this cursor. So you can see that the output of this what's this thing called? A switch capacitor filter. Switch capacitor filter it's kind of a digital, it's discretized in time. That was fun. Okay, so it seems like it is about 1/10 when we go to about 10 times F3dB. I don't think we can go 10 times higher in frequency because then we're going to run into this clock speed issue. But what else could we do? We could make F clock. Let's try going the other direction. So here, let me go back to 2 volts per division. I'm just making this up as I go, but let's try changing F clock to 300 kilohertz. I'm not even certain that this thing can do 300 kilohertz. I think maybe it can. So let's try 300 kilohertz. 300, yeah, I think it's like a 40 megahertz AWG. Let's try 300 kilohertz. And then we'll go back over here. Oh, look at that. Now we're back to about 45 degrees. You see? So this is our 1.6 kilohertz instead of 160 hertz. So you see, it's the same input signal, but the output signal is basically at f3 dB instead of being at 10 times f3 dB. Because you can see that we're now close to like 45 degrees. We're close to 1 over root 2 in amplitude. Even though, right, so we had this, the phenomenon that we saw at 160 hertz before, now we see at 1.6 kilohertz. So that's kind of neat. We didn't have to change any components to do that. We just changed this clock frequency. So that's kind of a neat feature of this algorithm, is that you can use the clock frequency to tune the corner frequency of the filter. And then I guess if we wanted to, now we could go up to 16 kilohertz. We come over here, and then we have to zoom in on the time axis again. And now we see a picture that qualitatively looks the same as the picture we saw a moment ago, except everything is 10 times faster. All right, anyway, so yeah, and if we go to like here, 200 millivolts per division, so you can see that the output is basically 1/10 the amplitude of the input. And then you can kind of see the steppiness. The steppiness is a little harder to see now because I think now we run into the limitations of the sampling rate of the oscilloscope itself. Okay, I think that was fun. I kind of liked the intuitive explanation. And I mean, another thing you could also look at this thing's step response. I guess, let's try that. So if we give it let's give this thing a square wave input instead of a sine wave input. Oh, another thing let's do is here. Now that we're here, let's look at the clock. You see, and now you can see the clock, and the clock lines up with the steppiness of the waveform. So that's kind of fun. Then let's go back to WaveGen here. Instead of a sine wave, let's give this, let's make it a square wave. And we should see the kind of the RC response to a square wave. I see. Okay, so this is like the kind of differentiator response to a square wave. This is like, see this circuit, the output, oh no, so not differentiator, sorry, integrator. Right, the output looks like the integral of the input if the output in magnitude, in the amplitude, is much smaller than the input. So let's now go down to a much lower frequency. So instead of 16 kilohertz, let's go to 1.6 kilohertz. And then we come over here, and I think we have to zoom out on the time axis. I'm making this up as I go, okay. And, now we want 2 volts per division. That's cool, look at that. So we see, like, it looks like the RC filter, like kind of like the shark tooth, so the RC filter, or is it a fin? Charging, discharging, charging, discharging, that's neat. And now let's even go to an order of magnitude lower frequency, and we should see that kind of classic RC charging, discharging curve. Let's try that. Here, let's see. Factor 10 might be too much, but that's 1.6 kilohertz. So let's do 0.16 kilohertz, 160 hertz. Okay, and then we'll go, I'm not sure we want to zoom out by a full factor of 10. Let's try it. Yeah, well, okay. See, then actually it looks exactly like a poorly tuned scope probe. But if we zoom in just a little bit, like this, then yeah, you do kind of see like the classic RC charging curve. That's kind of fun. And let me trigger on the other edge. And then you see the classic RC following curve. Yeah, so it's kind of neat. So with switching back and forth and 2 capacitors that are quite different from one another in size, well, I guess it's like a factor of 30, is that right? A factor of 30 or so in size. So this is like 1/3 of a nanofarad, and this is 10 nanofarads. Yeah, like about a factor of 30 apart. We see, we get the same behavior as an RC. Oh, you can't see that. You get the same behavior as the same behavior as an RC integrator. Oh, a moment ago I probably pointed at this and you couldn't see it. Anyway, you get the same behavior as you get from the RC integrator or the RC low pass filter. So I think that was fun. I like that. Okay, end of video. So this is the end of lab 20. I think all of these parts of lab 20 are worth kind of looking at and thinking about, but it takes time to build them on this EE board, so I don't think they're all worth taking the time to build. You can be choosy. You don't have to build any of them. But I think it's fun to ponder how each one of these things works, and then you can look at it in Circuit Lab. You can look at my video, and then if you want to choose one or two to build, choose the ones that look like the most fun to you. Okay, take care.